Hello guys, welcome back. Today we are diving deep into the design of SMPS using a flyback converter. Hold on tight because we are not just going to explain it like a boring classroom lecture. We are going to take this journey with a sparkle of fun. So, let's start. Let's know the MVP behind this video. Texas Instruments and SIMBA. Texas Instruments are pioneers of the semiconductor world. They make those tiny ICs which we see in the circuit boards. The team has provided the hardware evaluation board to test and understand an SMPS circuit. And the SIMBA is a power electronics simulation software with an awesome speed, accuracy, and simplicity, just like a flash. Last time we laid the groundwork of our SMPS adventure, and today we are leveling up for the design of a green mode power supply. Green, not because it's eco-friendly, although it is, but it's sleek and efficient. And we are designing it using UCC 28610 IC from TI. Now, our mission is to design a switch mode power supply which can handle the AC input voltage from 85 volts to 265 volts AC. Here we are talking about global domination, be it 110 volt AC or 230 volts. We need 12 volt as the output voltage with 10% error margin. So this voltage range would be around 10.2 volts to 13.2 volts. The accepted output voltage ripple would be 80 millivolts to 120 millivolts peak to peak. Our output current requirement would be around 2.1 amperes maximum, and it should take care all the way from 0 amperes. Also, our circuits got safety measures. We'll keep the input under voltage protection trigger up to 72 volts AC, and output over voltage trigger should be around 16 volts. Once we have locked in our choice of IC, the real heavy lifting starts. The calculation and circuit building. From the calculation sheet, we get the calculated values of the components. Based on that, we can do the selection. We already know how to select a MOSFET or a diode for our application. You can click on this card above to know more about this. After that, you can see all the calculations which are needed to design the circuit, and based on that, we can select our components. Selecting a transformer is the biggest hassle over here. We need to provide particular parameters to the manufacturer, and accordingly it will design a transformer based on our requirements. And finally, we have a schematic sheet where we can see what component values we need to design the circuit, including all of the logic components required for this IC. This is how the circuit would look like. We have AC input, rectifier, filter, this is the flyback converter design, and this is the auxiliary wiring for zero current detection and bias supply for the IC. And this is the feedback circuitry. Before jumping into the circuit design, we should do the simulation of the power converter based on our requirements. For this, I'm using SIMBA software. It has sleek GUI, we can integrate Python libraries, which is very handy feature. It does the thermal analysis as well, and my favorite part is that we can do multiple simulations together. Let's take our flyback SMPS. We have created multiple simulations of this flyback converter. All of these values are as per our design specs, except the IC. Instead of the controller IC, we have designed a closed loop PI control to get the feel. Also, unlike other power electronic simulation softwares, we can add the components parameters in the simulation as well, including thermal data. Now I will simulate all of these circuits and check the output voltage of them similarly. It might take some time. Now I can check the result of all of these simulation files all together, and I can compare these values as well. Check the current of this flyback transformer now. As you can see, it goes down to 0, and that's the beauty of discontinuous conduction mode. Now let's construct the hardware circuit of this SMPS. While construction, we'll see the significance of each pin of this IC and components used in this circuit. First pin is pin number 8, which is VDD pin. This is the supply pin for the IC. Next, pin number 7 is the ground pin. This terminal carries the full primary current of the SMPS. After that, we have a pin number 5 and pin number 6, which are VGG and DRV pins. These are responsible for driving external MOSFET. This pin provides a proper DC voltage for the gate of the external high voltage MOSFET, and this pin drives the source of the external MOSFET. After that, we have a feedback pin. As we saw in the last video, this IC accepts the current as a feedback. Next pin is the zero current detection pin. It has two functions. One, it senses the transformer reset based on the valid zero current detection signal. And second, it programs the output over voltage protection. Next pin is pin number 3, which is the current limit. This pin programs the peak primary inductor current, which is reached in the each switching cycle. As we know, the flyback transformer is just a coupled inductor. And final pin is the maximum on-time pin. The main functionality of this pin is to program maximum on-time of the internal driver. Now, let's go through the components which are used in this circuit. Here, we have diode bridge, input capacitor, transformer, MOSFET, Schottky diode, and output capacitors. These components form the main power stage of the converter. And these capacitors filter the high frequency noise. The input EMI filter is made up of this capacitor and inductor section. We can add surge current protection by adding a fuse. These all are the power converter components. Now we'll see the extra components which make our circuit intelligent and robust. Let's assume at the input side, we get a very high surge in the voltage, which might destroy our MOSFET because of the avalanche breakdown. If you don't know what it is, you can click here for a crash course. So, we need to protect this MOSFET. That's where a very famous solution called as RCD clamp circuit comes into picture. We connect a resistor, capacitor, and a diode in this fashion to minimize the stress on the MOSFET. Would you like to know how RCD clamp circuit helps to minimize the stress on the MOSFET? Then let me know in the comment section. I'll make a small video on this. After that, this resistor and capacitor make the snubber circuit. That's also a different topic. We need to provide the supply to the gate of the MOSFET. So this resistor supplies startup bias current to the VGG pin. We use Schottky diode to provide initial startup. The bias pin is provided by the auxiliary winding of the transformer, diode, and a bulk capacitor to the controller IC. And we connect a Zener diode for safety. Now, gate drive circuit is composed of gate drive resistor. This resistor and diode are used to provide a current path at turn off because the gate is shorted to the source of the MOSFET during each switching cycle. These capacitors are decoupling capacitors for VDD and VGG. This capacitor filters the common mode noise between primary and secondary sides. This capacitor reduces the output voltage ripple. These two resistors program the over-voltage threshold. And this capacitor can be used to add a small delay to ZCD. This resistor programs the maximum on time of the HV MOSFET. R4 sets the maximum value for the peak primary current. These resistor and a capacitor are the part of a feedback circuitry from the primary side. And these resistor with a diode are part of a secondary feedback circuit. Once we turn on the AC supply, we get here the DC output voltage. This supply goes to the primary of the transformer and then to the MOSFET. Well, this supply is very high. We cannot directly connect this to the controller IC. The IC can only support up to 25 volt max. So, how can we do it? Well, to remove this roadblock, we can make a separate low power winding just to provide enough power for the IC to run, which is achieved by this auxiliary winding. Both the secondary winding and auxiliary windings get the energy from the primary winding only. The output of this aux winding is given to the VDD pin via diode and a bulk capacitor, which provide filter DC output. This Zener diode here maintains the bias voltage on VDD below the maximum rating. After that, the IC would start switching. But before it starts, the MOT pin detects its resistor value, which is connected to the ground, which decides the maximum on time of the circuit. So it adds some delay. After that, the IC starts switching. Its switching frequency and peak current are modulated based on the FB pin current. The FB pin current is determined by the feedback loop design and output loading condition. This feedback loop is made up of taking the voltage feedback from the secondary, adding an optocoupler between primary and secondary for isolation. Based on this feedback voltage, the optocoupler sends a signal to this feedback pin. This signal goes to the internal modulator. As the output voltage changes, the current flowing through this feedback path should change and internal circuit detects it. We should provide AC filtering to this output of the optocoupler at the FB pin to minimize any noise. This optocoupler takes the output feedback from primary to secondary without any physical connection. So that's the beauty of isolation. There are three different operation modes of this converter: frequency modulation mode, current modulation mode, and green mode to achieve better efficiency. So during normal operation, that means at heavy load, the flyback converter works with the frequency modulation mode. In medium to light load, the converter operates in fixed switching frequency with peak current modulation current mode. Fancy words. Once the load becomes too light, the converter operates in fixed frequency and fixed current mode. Because of this converter gives high efficiency at different load conditions. This PWM IC senses the current flowing through the primary using a DRV pin. Because the whole current flows through this path, this current is compared with the current limit function that we program using this pin. Finally, we have a section of zero current detection. Zero crossing is detected using a resistive divider across this auxiliary winding. This winding operates in phase with the output. Using the same pin, we can also detect the overvoltage. Well, we understood how to design this circuit and how it works. Now, let's see its actual version. There is no satisfaction of a design until and unless we test it in real life. So, as per the design, I already have an evaluation board for Flyback SMPS using UCC 28610 IC from TI. This is the input section with rectifier and filter. This is the flyback transformer, the optocoupler, this is the main MOSFET, this is the Schottky diode at the output. These are the output capacitors, and on the bottom side of the PCB, we have the heart of the circuit, which is PWM IC, and its peripheral circuits. Let's wire it up and test it out. We are connecting the input to the AC source. I have connected a resistor load at the output. Now I'll turn on the measurement equipment and give supply to this board. So as you can see, the output is around 12 volts. And this is how the switching of the MOSFET would look like. So this particular rectifier converts AC into pulsating DC. Then we get a filtered DC output at the input of this flyback converter. And then after that, the flyback converter steps down this output voltage. Well, I cannot change the input voltage here because it is directly connected to the grid. But I can test this circuit with different load values and see how the switching of this MOSFET would change based on the load requirements. Now I will turn on the load. As you can see, the output current is around 2 amperes. And there is output voltage change. And because of the loading current, there is a change in the output. This is the voltage of the MOSFET, which is between drain to source. Now I will change the load resistance and see how these waveforms behave. So I am changing this resistance value, and as you can see, as I am changing the resistance value, the switching of the MOSFET is also changing because it is adapting to the output requirement. And if I go beyond certain value, the IC will try to shut down itself because of the overcurrent. So this is how we can design an SMPS according to our requirements. Well, it's a wrap. If you like SIMBA, the simulation software for power electronics, then you can request a trial version. I have added the link in the description. The installation process is very easy and straightforward. And right beside that, there is a subscribe button. Don't forget to hit that as well. I'll see you in the next such amazing video. Till then, stay hungry, stay foolish.